All right, you guys, on our day 5 notes, we're going to be doing composite solids, which means we did this in unit 6, where we put 2 or 3 2D shapes together, and then you have to find the total area. Well, we're doing the same thing in unit 7, but we're doing it with 3D shapes. So we're putting 2 or more 3D shapes together to form a composite solid, and then you have to find the total volume or surface area of that new solid. We've been sprinkling these throughout the unit, so this isn't the first time we've seen these. We've had quite a few problems that were like a cylinder with a cylinder cut out of the middle, so we subtract. So we're going to be doing volume and surface area. Volume is always going to be the easiest one, because if you're stacking shapes on top of each other, well, then you're just finding the individual volumes and adding them together. Or you might be digging a hole out of a 3D shape, in which case you're just going to find the volumes and subtract them, right? Because, for example, on this number 2, we've got a cube and we're digging out a cone-shaped hole. So we're subtracting volume instead of adding it, right? So volume tends to be pretty easy. Surface area is a little more complex because you have to make sure that you're only using the surfaces that are touching air, and you have to keep track of what's not there and what is there, especially if you're digging out a hole. Anyway, so we'll get to that one here in just a second. We're going to do this one first. So we are going to start with this composite, which is clearly a cone with a half sphere. Now, what I like to do, and you don't have to do this if you don't want to, but I'm going to write cone, and we're clearly adding the half sphere. Or you could say hemisphere or semisphere, but I like the half because that's what I'm going to write in my formula. So when we do volume, so we want the volume of a cone. So I like to write my formulas down, of course. Pi 1/3 pi r square h plus half. And then, of course, the volume of a sphere formula is 4/3 pi r cubed. Okay, so now that I have everything in there, all I need is the radius and the height, which are both given to me in the picture, which is super nice. So I can just go ahead and plug all those numbers in. So the radius is 6, the height is 17, plus I'm going to go ahead and take half of the 4/3, which is 2/3, and then I can just do pi 6 cubed. And then I'm just going to use my calculator to simplify each one of these pi terms. So give me 1 second. I'm going to type this in. So 1/3 times 6 squared times 17. And I'm getting 204 pi for the first term. And then I'm taking 2/3 of 6 cubed, which is 144 pi. And of course, I can add these together, right? They're both pi terms. So that's going to give me 348 pi. And our units on that, of course, are going to be feet cubed. Right, and there you have it, right? There's the total volume of the composite solid. Again, volume is always going to be your easiest one because you're just adding or subtracting volumes, okay? All right, I'm going to move him kind of off to the side over here. So, goodness, so I can have some space for the surface area next. All right, so when we do surface area, we're going to want to make sure that we are doing just what's touching the surface. So as far as the cone goes, right, the only part of the cone that is touching the surface is just the lateral area. So obviously his base, right, the circle base is not touching air, so he is not on the surface. So I do not want to do total surface area. So I'm just going to do pi RL for the lateral of the cone. And then, of course, I want the surface area of the sphere, but it's only half a sphere. So I'm going to add half of the 4 pi r squared surface area. And that should do it, right? So here we go. So pi, obviously the radius is still 6. Now you'll notice we're running into L, which is our slant height, which they did not give us. So I'm going to need to go off to the side here and do a quick little Pythagorean theorem with our right triangle to find our slant height, right? Because here's our slant height. So we're going to do 6 squared plus 17 squared equals L squared. Okay, I'm going to type that in. 6 squared plus 17 squared. That gives us 325. And obviously L is going to be the square root of that, which is not a perfect square. That's okay. So I'm going to go over here, right? And obviously 25 goes into that 13 times, which is nice because 13 is prime, which means it just leaves us with the 2 5s from the 25, right? Which means our simplified lateral height or slant height is 5 root 13. Yay. All right, so now that I have the 5 root 13, I'm going to come over here and put that in for L. And then plus, obviously, half of 4 is 2. So 2 pi 6 squared. All right, I'm going to do my math there. So now this is going to be a weird term because I have a pi and a square root. So whenever we write that down, we're going to multiply the 6 times 5, which gives us 30. Then we put the pi, then we put the square root. When you have a square root answer, it should always be at the back. Never put the pi behind it because then it's like, is it under there? Is it not under there? Right? So square roots should always be at the back of the term. And then plus, and then 6 squared is 36 times 2 is going to give us 72 pi. And these are not like terms, right? Because this guy's a pi root 13 term and this guy's just a pi term. So since these are not like terms, we are done as far as exact answers. Now, obviously, if it said round to the nearest tenth, then we would type that in, okay? And there you have it, right? There's the surface area. Now, that one wasn't too bad, right? We're going to kind of up the difficulty as we go a little bit, okay? All right. The next one also wants us to find the volume and the surface area. Okay, so I'm going to start with volume because it's the easiest. So clearly, we're going to do cube minus cone, right? Because it's a cube with a cone-shaped hole. And the cone does go all the way through the cube, and we can tell that because he has the same height as the cube. So those are just kind of little things to notice. All right, so I like to throw my formulas in. So don't forget the volume of a cube is side cubed minus, and then the volume of a cone is 1/3 pi r squared h. All right, so we just got to throw our numbers in. So 6 cubed minus 1/3 pi, and the cone has a radius of 2, but also a height of 6, like the cube, just like we talked about a second ago. Now, clearly, these are not going to be like terms, and we knew that ahead of time because circle things and prism things do not play nicely with each other, right? Because one's going to be pi term and one is not. So we know we're going to end up with a binomial answer when we see something circular with a prism. Right, and so anyway, we can start typing that in our calculator. So, of course, we're going to get 216 minus, and that's going to give us, what, 8 pi? And that is going to be our final answer for our volume. Put our units on there, and voila, all done. All right, I'm going to scooch that over here again, give myself some room for the surface area. Now, again, everybody's brain thinks a little bit differently when it comes to surface area. Okay, so you can piece this all together as however you want to, as long as you get all the surfaces, right? Like I know I have this, the left side, the right side, the bottom, the front, the top, right? So you can piece it together however you want to. So how I might set up my formula and how my brain thinks about how to piece it together may not be the same as the way that your brain would, and that's totally okay. All right, so the first thing I'm going to do is deal with my cube, because almost the entire cube is on the surface except this circular hole. There is a cone-shaped hole, so that is blank. Like that's just air right there. So I need to make sure I account for that. So when I do my total surface area for my cube, I'm going to use 6s cubed, which is the total surface area because there's 6 faces. But I'm going to subtract the circle area that is a vacant hole in the top. Okay. And that's going to take care of the hole that's in the top of my cube. Okay. Hoping that makes sense. And then you have to keep in mind, anytime you dig a hole out of something, you're actually, you're actually creating more surface area inside the hole, right? Because now all the surrounding edges on the inside of the hole, they're now touching air. And of course, the inside of the hole is a cone, and only the wraparound part of the cone is a surface. So that would be the lateral surface area. So we need to add on the lateral surface area, of the inner cone hole. Okay, so cube minus the circular hole plus adding on the inside of the cone hole. And that should take care of it. All right, so now we can just fill in numbers, right? So 6 and then another 6 squared minus pi. The radius of our circle up top is 2 plus pi, radius of 2 again. And then you'll notice that darn slant height again, which they did not give us, right? So we need to go find this slant height L right here with another little Pythagorean theorem. Let's see. I'm going to scooch this down a little bit so I can do the Pythagorean theorem there at the top. So that's going to give us 2 squared plus 6 squared equals L squared. That's going to give us 4 plus 36, so 40. And that's just 4 times 10, so 2 root 10 is going to be our slant height. So now I know that I'm going to put 2 root 10 in my formula over here. All right, now I just got to clean up all this mess, right? I already know 6 times 6 squared, which is 6 cubed, is 216, just like it was for the volume, minus 4 pi plus 4 pi root 10. And unfortunately, none of these terms are like terms, right? Because we have a constant, a pi term, and a pi root 10 term. So that's going to be our final answer. And then, of course, we want to put our units on there. And voila, there you go. Surface area of this composite. All right, now that we're kind of catching on to the surface area, we're going to do 2 more problems with and we're just going to do surface area. This one would be really easy to do volume. We've actually seen this like 3 times now on homeworks and quizzes, right? If I wanted to find the volume of this, I would just find the volume of the outside cylinder and I would subtract the volume of the inner cylinder, and that would give us our total volume. But surface area is different, right? Again, how you want to piece this together is totally up to you. I know in class, most students thought of it differently than I would have done it, but we can talk about that. So I'm going to do it the way that most students in class kind of saw this. So most students, when they first see this, they see the lateral surface area of each cylinder, right? So I know that this outside part, right, this is the lateral surface area of the big cylinder. But then, because we dug a hole through it, I've now created more lateral surface area on the inside ring. So we have to have both lateral areas, okay? So I know the lateral surface area of a cylinder is 2 pi RH. Plus, I'm going to do another 2 pi RH. And just for good measure, I'm going to write, just so I can keep track, that that's the big lateral surface area. And this is the inner, or the small cylinder's lateral surface area. And that should take care of that. But we have more surface area, right? So I got to keep adding. So the next thing, sorry about that. The next thing I notice is that I have these donut shapes, right? These circles within circles going on the top. I'm just going to kind of, take forever to make this happen, right? So if I'm doing the area of this top circle donut shape, then that means I'm going to be doing big circle minus little circles area, and that should give me the area what's left, right, after we subtract out that inner circle. But you also have to keep in mind that there's one of these on the top and there's one of these on the bottom. So I'm going to multiply by 2 because there's one on top and one on bottom. And I'm going to do pi r squared minus pi r squared. Right? So I'm doing, again, I'm going to kind of label this. This is big circle minus the small circle. And that will give me that donut shape. So I subtract the area of the two circles. That's going to give me the area of that green shaded region. But of course, there's a second one on the bottom, so I'm going to double that number. All right. I hope that makes sense to everybody. Okay, here we go. Let's start putting some numbers in. They gave us everything we need, right? So the hard part is just getting yourself a land map, like a map of where to go and where to plug your numbers into. So here we go. 2 pi. So let's see, the bigger cylinder up top, it tells us has a radius of 8. And they both, of course, have a height of 4. Plus the inner ring, 2 pi, and it tells us the radius is 3, height of 4. Plus the two donutty circles, which would be pi 8 squared minus pi 3 squared. That is a lot of numbers, right? But we just got to clean that up. All right, let's see. It's going to give me 32 times 2. So this is going to give me 64 pi for the outer lateral area plus 24 pi for the inner lateral area plus 2 times, what is that going to give me? 64 pi minus 9 pi. All right, and again, I'm just going to do this one step at a time so I don't lose anybody, but you're more than welcome to quicken this up a little bit. Right, so that's going to be 2 times, 55 pi. All right, and again, I know I could just go ahead and add the first 2, but I'm just going to go ahead and wait till I have all 3 terms. Right, so that's going to give me 110 pi. Right, so I just like to see the 3 terms, right? So we've got the lateral outside ring, the lateral wraparound part of the outside, the wraparound part of the inside, and then the total of the top and bottom little donut shapes. Right? Yay, and they're all pi terms. So we're going to go ahead and add all of those together. And we should be getting 198 pi. And they didn't really give us units, but I'm just going to write u squared. Now, if you didn't like how I pieced that together, you could have also done total surface area. Right? If you acted as if this was filled in and you did the total surface area of the big cylinder and then just subtracted the 2 circles on the top and the bottom and then added the lateral on the inside, you would have gotten the exact same answer, okay, at the end of the problem. All right, let's do one more. Well, we have 2 more, I guess. All right, find the total surface area of this composite figure. This is very similar to this one, kind of, because we have that, we had a cone-shaped hole, so there's a circle taken out. We have the same thing going on here because we have another cube. And please notice on the top of the cube, it's the same thing is happening, right? Not all the surface area of the cube is on the surface because when you stack a cylinder on top, this circle right here is no longer on the surface. So we have to account for that when we set up our formula. So I'm kind of going to do the same thing. I'm going to use the 6s squared formula as if I could see all of the surface area of the cube, but I'm going to have to subtract the pi r squared, right? That green part here. I'm going to color code it so you can kind of follow it in the picture. All right, and then now I have to take into account the cylinder. Well, only the wraparound part of the cylinder, right? So we're going to take on the lateral surface area. So we're going to add 2 pi RH, and then we want to add the top base only because only one circle base is actually being added to the surface. And there you have it, right? There's a nice little game plan to make sure we've got all the surfaces accounted for. And I tried to kind of color code that so you can follow what's going where. Now, if you happen to catch on that you have a minus pi r squared and a positive pi r squared, and those are just going to cancel each other out, well, then that's just going to make lighter work for you, and you can just cross those out. So really, right, we're just doing 6s squared, where the side is 5, and the 2 pi rh. And the radius is 2 because notice the entire diameter is drawn, which means they're pointing to the entire diameter, okay? And then, of course, the height of the cylinder is 4. All right, so let's see. Let's do some math. 25 times 6 is going to give us 150 plus 16 pi. And that should do it. Square inches. All right, hopefully that one makes sense. All right, let's move on to, I believe, our last one, and then we're gonna switch topics here just a little bit. All right, so this says you have a prop for a play that looks like this, and they want to paint everything on the surface except the bottom, right? There's no need to paint the bottom because no one's going to see the bottom, right? So we want to make sure that we're finding the surface area of just what you would see on the outside. All right, so here we go. Let me double check. Let's see. There we go. So clearly we have a rectangular prism. Now remember, when you have a rectangular prism, you get to kind of choose which one is the base. I would clearly choose the bottom as the base. That's a little crooked, but that's okay. Right, so I'm going to use this as my base. So the base is a 6 by 5 rectangle, right? And then clearly the height is the 8.5, right? So that's how I'm going to set my prism up. So let's see, total surface area. I only want the lateral surface area though, because the bottom isn't getting painted and the top is certainly not getting painted because the top has something on top of it. So only the lateral surface area of the prism is actually on the outside that's going to be painted. And so that's your formula pH, right? And then plus, now we need to recognize that this guy on the top, right, he is half of a cylinder. Okay, and we want exactly half of the total surface area because we have half the wraparound part, we have half a base here, and we have half a base on the back, right? And all of that is getting painted. So we're going to add half of the surface area of a cylinder. So 2 pi RH plus 2 pi R squared. And yes, if you want to, you can actually cancel out the halves with the 2. Right? But I'm just going to leave it for now. All right, so let's fill in some stuff. So remember, capital P means perimeter of the base. So I'm clearly using the 6 by 5 base. So that is 11 plus 11 more. So my perimeter is 22, and the height of my prism is the 8.5. Plus the 1/2, and then plugging in everything about our cylinder. So 2 pi, the radius is 3. Now the height of the cylinder, remember, is this from circle base to circle base. And we know that's 5 because that's also the depth of the prism, right? So the height of the cylinder is 5 plus 2 pi radius squared. All right, now we just have to clean all of that mess up. So 22 times 8.5 is 187 plus, and again, I'm going to go ahead and do this baby step in so I don't lose anybody. So 6 times 5 is 30 pi plus 9 pi. All right, so 187 plus, I'm going to do this, obviously 30 plus 18 is 48. If I take half of 48 pi, I'm going to get 24 pi. Right, and that is going to be, now I did notice up here it says to the nearest foot, right? So I am going to put this in my calculator. This is my exact answer, of course, but when they say to the nearest foot, right, that means we're going to round and insert the pi and just type all that in our calculator. So my final answer, when I type that in my calculator, is about 262 square feet. Okay, so just make sure you're paying attention to the directions, whether it asks you to round or not. All right, moving on. Number 6 is not necessarily, it's not a composite problem. It is a shape within a shape, but it's not really a volume or surface area problem for composites. It's just you're using one shape's information to give you information about the other shape so you can find its volume. That's kind of confusing. So let me just show you what I mean. So on this problem, it says a square pyramid is inscribed in a cone. Okay, I'm going to draw that over here as best I can. I'm going to draw it pretty big so you can kind of see all the moving parts. Sorry, I don't like it when it's crooked. There, that's better. Okay, so here's my cone. And I'm going to draw a square pyramid inside of that cone. Now, if it's inscribed, remember that means that it has to be touching all the vertices of the square base have to be touching the circle. That doesn't look very square-like, but just bear with me. All right, and then, of course, it also has to have the same height. So it has to be the biggest pyramid you can draw inside that's touching the circumference of the circle base and going all the way up to the top, right? That's what inscribed means. I can't just have like a tiny little pyramid like floating on the inside, right? It has to be taking up as much space as possible. All right, so that's kind of what we're dealing with, right? A square pyramid inscribed in a cone. Now, this is where it gets kind of weird because it says the cone has a radius of 4. Now, remember, you can draw a radius anywhere you want, right? Because it's like radius, 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 radius. We are used to kicking our radiuses out to the side like this, but is that going to be helpful to me? No, and that's really the whole point of this question. I don't want to draw my radius right here because that's not a part of my pyramid. So if I can draw my radius anywhere, I'm going to draw it here. Because not only is that radius of 4 a radius of my circle, but it's also a radius of my square base. Okay. And then, of course, if you want, which you should, we're going to drop the apothem, right? And this is our apothem right here. And we're back to kind of day 2's homework, right? Where we have our little right triangle inside of our regular polygon base. There we go. And I'm going to go ahead and, oh, sorry, my eraser's in giant mode. I'm going to go ahead and label my apothem because I'm probably going to need it. So remember, this is a 45, 45, 90 right triangle, which means my apothem is going to be 2 root 2. Right? Because we have to divide by the root of 2 and then rationalize the denominator, and that gets us 2 root 2. All right, let's see what else. It also says we have a height of 4. Okay, so I'm going to drop my height, right? And that's 4. All right, that's a lot of labels, right? So then it says, find the volume of the pyramid. Okay, so again, notice this isn't really a composite question. We're just using the information of the cone to help us get enough information about the pyramid to find its volume. Okay, so here we go. Volume of a pyramid is 1/3 BH, where the capital B is the area of the square base. Now, I'm going to go ahead and just use the area equals 1/2 apothem times perimeter since I already have that information. You can, of course, just use side times side if you want to. It's going to give us the same answer. So 1/2, my apothem is 2 root 2. And, of course, my perimeter, remember this is an isosceles triangle. So that means the whole side length is 4 root 2. And there's 4 of them, which means my perimeter is 16 root 2. Woof. All right. So that means again, you can shoot all of that in your calculator if you want to. Just make sure you put it in parentheses, right? And so that's this. Remember, the square root of 2 times the square root of 2 is going to give us 2. So half of 2 gives us 1. So we're really just left with 2 times 16, which is 32. And again, you can find the square just doing side squared. Once you find the side length, you're going to get the exact same answer. So now that I know the area of the base is 32, I'm going to come over here and put that in. And then, of course, the height of our pyramid is the same as the height of our cone. Now, that's not a very friendly number to take a third of, which means if I type that in my calculator and hit math, enter if I need to, right, then I'm going to get 128 thirds. And that's going to be meters cubed. Okay, so there's a few of those on your homework, right? Inscribing shapes inside of other shapes and using that information to help you out. All right, the last question here says, find the slant height of the cone and the pyramid. Okay, so here we go. I'm going to do the pyramid first. Okay, so keep in mind on the pyramid, let me go here. The slant height, my picture is going to get really crazy here. Remember, the slant height is the height of the lateral face. So I'm going to go ahead and kick out and make my right triangle over on the right side like I normally would all the way back from day 2. So I'm going to look at this picture, and then this is my slant height right here. Let me draw a line to it because there's just so much happening. There we go. All right, so here's my right triangle. And the awesome thing is this right here is just another apothem, right? And I already know he's 2 root 2 because this is also an apothem, right? So it doesn't matter which apothem I draw, right? It's all going to give me 2 root 2. And there you go. So that's going to help me just do a quick little Pythagorean theorem. So I'm going to be able to do 4 squared plus 2 root 2 squared equals our slant height squared. That's going to give us 16. I don't know, square radical expression. You have to square everybody. So that's going to give us 4 times 2, which is 8. Oops. And again, you can type that in your calculator if you want. Just make sure you use parentheses. And let's see, that's going to add to give us 24. And then we're going to take the square root, which that's just 4 times 6. So 2 root 6. And that would be meters. All right, so that's going to be the slant height of our pyramid. Now, of course, the slant height of the pyramid is not going to be the same as the slant height of the cone, right? Because you can clearly see that the slant height is inside of the figure, whereas the slant height of the cone is this guy, right? But we need to find him. Well, that slant height, I'm going to erase that label right there. Goodness, I feel like I need another color. Let me grab some like turquoise or something. There we go. All right, so do you happen to notice, I'm going to go back over here on the left side. This edge of the pyramid, right, is going along the entire face of the cone. So this right triangle, right, so I'm so hoping y'all can follow that. There's a lot happening in this picture. Let me go a little lighter than that. There we go. Right, so here is the right triangle that will help us find the lateral or the slant height of the cone, right? Because it's using the edge of the pyramid. So it's just a 4 by 4 right isosceles triangle, which the cool thing is, if you recognize that it's a 4 by 4 right isosceles triangle, then you can just tell me the answer right away, right? Because it's a special right. If you need to, of course, you can do the Pythagorean theorem to prove it, right? So we're going to get 4 squared plus 4 squared equals L squared. All right, that's going to give us 32 equals L squared. And when we square root, what do you know? We're going to get 4 root 2, which makes perfect sense because it's a 45, 45, 90 triangle, right? And then, of course, I'm going to add meters to that. All right. Kind of a lot going on there. All right, that's pretty much it for composites. There's one more tiny little thing we're going to learn about today, and that's cross sections. And I'm not sure if you've heard of cross sections before, but a cross section is basically when you slice through a 3-dimensional object, like with a plane, what 2-dimensional polygon is created at that plane or at that cross section. So what I kind of like to imagine, and this might sound a little silly, but we're only going to be doing perpendicular and vertical cross sections. There's also diagonal cross sections, but we don't really talk about those. You'll learn more about those when you get to Algebra 2. So we're just going to worry about parallel. And when I say parallel, I mean parallel to the bases, right? So like in a cylinder, these are my bases. So if I slice through it parallel to the bases, I'm talking about horizontal slices in this picture. Okay. Oops. So here we go. I like to kind of imagine that my three-dimensional shape is like a birthday cake, right? So imagine that this was your birthday cake. Here's the candle, right? And so we're going to decide to slice it horizontally, right? Which I know would be really, really weird, right? But if I were to take a knife and slice through it perfectly horizontally so that I was parallel to the bases every time, and then I plopped a piece of cake on everybody's plate, like what shape would everybody's piece of cake be, right? And clearly everybody's piece of cake would be a perfect circle, and everyone would get the exact same size circle because that's what a cylinder is. It's just a whole bunch of infinite circles stacked on top of each other, right? So if I was to slice through it, I'm going to get a cross section that is a circle every time if I go parallel to the bases. Okay, I'm going to try to draw that just so you can have a visual, maybe. All right, I'm going to stretch that out. There we go. All right, and so hopefully you can see, right, if this was how I sliced through my cylinder, right, and I opened it up, right, or gave that slice away, right, it would be a circle. All right, and then our other cross section is going to be if I went perpendicular to the base. Meaning, what if, again, I'm going to pretend this is my birthday cake. What if I were to slice here? Oh, wow, that's a horribly crooked line. What if I were to slice my cake here, and then here, and then here, right? And I made all of these vertical slices perpendicular to the bases, right? And then gave everyone the slice. And the question is, what shape would everyone's slice be, right? And I'm hoping you're thinking to yourself, well, I believe that would be a rectangle, right? And it would, right? And that kind of goes back to our notes from the other day where we talked about revolutions. Remember, if you take a rectangle and you spin it around an axis, right, it creates a cylinder. We're kind of undoing that here when we slice through it, right? So basically, if I cut it down, I'm going to try to give you a better visual. I'm not the best three-dimensional person here, right? And so there you can kind of see the rectangle that's being created, right, when we slice perfectly vertical or perpendicular to the bases, right? So every perpendicular slice is going to be a rectangle. Okay. Oh, we thought it. All right, we're going to talk about a cone, right? So if I have a cone, again, we're going to talk about slicing it parallel to the base. So again, imagine it's a birthday cake, which this would be a very odd-shaped birthday cake, but just bear with me. If I was to slice horizontally through a cone, right? Again, what shaped piece of cake would everyone be getting, right? And I'm hoping you're saying a circle, right? Because the base is a circle. So if I slice parallel to the base of a circle, I'm going to get circles every time. Now, it's not really fair, though, because obviously the guy at the top of the cake is just going to get a tiny little circle, right? And then the guy at the bottom of the cake, or closer to the bottom, is going to get a much bigger piece of cake, right? So unlike the cylinder, we're going to have varying sizes of circle cross sections, right? And that's okay. Maybe, right? So anytime I slice through parallel to the base, my cross section is going to be the same shape as the base, which is a circle, again, in this case. Now, what if I go perpendicular to the base, right? But I added a through the vertex, right? So I'm only talking about if I were to slice directly through the vertex, perpendicular through the base, and I opened it up, right? What shape would I be looking at, right? And I'm hoping you're saying a triangle, right? Which kind of goes back to our conversation the other day, right? About how triangles that revolve around an axis create a cone, right? So we're just kind of taking that backwards, right? So if I were to slice through this guy, I'm going to end up with a perfect triangle, but only if I go through the vertex, right? If I slice through the side, right, and not through the vertex, well, then that's a totally different animal, right? That's going to start giving me weird curves, right? And so those are going to be parabolas and hyperbolas, which again, you'll talk about in algebra 2. All right, and then our very last one is a sphere, which I think we can all, it doesn't really matter because spheres don't have bases. So it doesn't really matter how I slice through a sphere. Every single time I do so, I'm clearly going to get a circle, right? And it's never an oval. It's always a perfect circle. But of course, kind of like the cone, right? The closer I get towards the edge, right, the smaller the circle. And of course, the biggest circle, right, is going to be the one that passes through and includes the diameter. We call this the great circle because he is the largest possible cross-section that you can get in a sphere. But either way you slice it, you're going to get a circle. Okay? So that is cross sections, right? Slicing through a three-dimensional solid and asking yourself what 2D shape you end up with. All right, you guys, I hope that makes sense, and I hope you feel comfortable on your homework. If not, you can always come in and ask questions. All right, see you later.